Hi, I'm Sam Ben Yaakov. This presentation is entitled Intuitive Explanation of the Dual Active Bridge. The presentation is based in part on a paper, DSP Control of Gyrator Behaved Switch Mode Converter, published in 2008, presented in a conference, and also in part some material from two other papers which are printed here. Now, this paper, which is the key one, is also printed in the page of this video, and also there is a link for a download of this paper. So, why dual active bridge? What are the benefits, or what's the advantage of using it? Well, it has a wide voltage transfer ratio, could be isolated, could be built in an isolated way. It achieves zero voltage switching, can be designed for high power, could be also bidirectional, that is, the power goes from one way, from a source to a load and then back. It behaves like a current source, and in fact it behaves like a gyrator. And I'm going to discuss all these issues in the next slides. Now, what is a dual active bridge, and what would be an application which is suitable for it? A current application, which is kind of great interest now, is an onboard charger for electric vehicles, and in particular the vehicle to grid capability version. That is, a charger that can charge a battery and then take energy from the battery and feed it back to the line. What we see here is the rectifier. This is actually an active power factor correction stage, which I'm not going into any detail on it, and it is used in the forward direction in order to rectify the AC signal of the grid, and also to provide low harmonics for the current, that is active power factor correction. And then we have the dual active bridge. This is these two bridges connected in this case by a transformer and an inductor, which is very important for the operation. This is the bus here, and then there is a rectification by the second bridge, in fact, and here's the battery which the system is feeding. Now, on the reverse direction, we have another bridge here which is pumping the power into the transformer this side, and then this is actually rectified here to get a DC again, and then this, which was used before as a rectifier, is now used actually as a inverter, which produces a sinusoidal current waveform which is fed to the line. So this is a very typical application of a dual bridge, a dual active bridge, which is now of great interest today. So what is a dual active bridge? We do have dual bridges. That is, there are one bridge here for transistors, and there is another bridge here for transistors too. I'm showing here first the non-isolated version, that there's no transformer in between. In this case, of course, this, let's say, line here is jumping all over the place because you know, there's a switching here, and so in some application you can use this version. Also, in this case, we have a voltage source, could be a battery, that say we are charging or transferring energy from this side to this side. It could be either way. Now, in this case, the battery is actually getting all the power in this case, and obviously there's a ripple here, so there is a need for a capacitor and maybe an extra filter if this is a battery. Now here is an isolated version. Basically it's the same. We have now a voltage source, there's a filter capacitor, this is the bus on the input side, a 1-to-N transformer. This is now the inductance or inductor, which is actually the leakage inductance. It's shown here that the leakage inductor inductance is used in lieu of actually a component like a discrete component to be put here. It has advantages and disadvantages. I'm not going to into this in this video here, just to say that we need an inductor here. We have another bridge at the output, and then we can have a battery or a source like a voltage source, and here is a filter for the ripple that is going to be here. Now the operation of this system hinges on having this primary or input side bridge operating in a 50%, you must say, duty cycle. That is 2 transistor and then 2 transistor. So this is producing the VAB, that is the voltage between here and here, is a square wave. And then we have another bridge here which is also toggled like this, except that there is a phase shift between the primary side and the secondary side. Like these 2 transistor and 4 transistor are operating again 50% duty cycle, but they start this S1, S4, this S1 and 4 start here, while S5, S8, S5, S8 starts a bit later. As a result, we have a situation in which voltage that is reflected back to the input is not in exact phase, that is a little bit shifted. So we'll see it in a minute, one portion of the time it's 1 voltage, then it will switch over to the reverse, because if instead of these two will operate, S5, S6 and S7 instead of S5 and S8. This is actually flipping over the load here. So we have now a phase shift, as it is called, and I'm now showing one way of operation. We'll later on discuss other ways of operation. This is the most common one, the most popular one. These are run at 50%, you might say. There is a phase shift between one and the other. Obviously, when you turn on, say, S1, S4, and then you turn on S2 and S3, you have to have a dead time. Otherwise, you'll have a shoot through here. So here it doesn't show, but obviously when you turn off, say, S1, S4, S1, S4, and before you turn on S2, S3, you do need some delay, which is a dead time, at which time actually the diode of the transistor, I'll talk about it later, is conducting. So this is the very basic structure here. Let me go a little bit more in sort of to get a feeling of what's going on. So for example, if S1, S4 is conducting, here it is, then S1 and 4 is high, S2 and 3 are low, and in this particular case, S6 and 7 are high. These are high, so therefore we get now a reflected voltage which is actually the reverse of the input, so the difference between V1 and the other side of the inductor is large, so here it exhibits itself as a large difference. This is the voltage on the inductor. Now later on, S5 and S8, S5 and S8 now flip over, and they bring now or reverse the polarity here, and consequently what the inductor is seeing is just the difference between here and the reflected voltage, not the reverse of it. So the difference is smaller. Here it is. This is the difference. And in each case, we have, of course, a change in the current of the inductor, which is a function of the voltage across it, V over L. So in the first part, I didn't mention it, it's a fast rise because the voltage is high, while here the difference is small, so the rise is shorter. So this is now the waveform where we can go one step forward and see again. This is now the reverse side, and therefore the current will be going down. So this is the way this thing operates with 50%, 50%, and a phase shift between them to generate these waveform and of the voltage across the inductor, and therefore the current that is flowing through the inductor, and eventually will go into the load. We'll see it in a minute. Now obviously, if I change the phase shift, that is, I increase it, then the current will go much higher, and this I'm not going to fine detail, because I'm going to discuss it later. This increase will increase the output current to the load. So the control here is by this phase between the primary and the secondary bridges. So in order to understand in an intuitive way, rather than going into pages and pages of equations, in order to understand what is really going on and what is really affecting the transfer ratio between input and output, let's do an experiment. Let's short the output and then let the system run. Okay? Obviously, if you short the output, no matter which pair is conducting, it's a short. So you have a short here. Okay? Now, if you have a short and you have a square wave on an inductor, then this what will happen. The voltage is a square wave. When the voltage is high, say positive, then the current will go up. When it is negative, it's going down. In steady state, it will be like triangular. Plus and minus peaks are the same, and the slope here is obviously V1 over L. V1 over this L here, I didn't mark it, is the slope, and this will just go on and on. This is what we'll see at the inductor, a triangular waveform. So let's now go one step farther. Here we have the same situation. There is a short at the output. However, I'm now toggling the switches in a certain way. And here, in this particular case, I'm in phase, toggling the secondary, that is the output bridge, such that QB1, QB4, B1, B4 are in phase with this, and then QB2 and QB should be B3 are when we have the reverse voltage here. Okay, so if now I'm looking at the current that is flowing, I see here the same current that I see at the primary. This is the primary here, and the average current here is 0, because this is the triangle. This is like the short experiment that we have seen. This is VAB, and it's negative starting here, going positive, then negative, etc. So the average here is 0, because this is equal to this. Doesn't look this way, but that's the way I've drawn it. And the same thing goes here. The average of I2 is 0, because here it's negative, here it's positive, and same thing goes for the second half cycle. Okay. Now, however, suppose I'm shifting the toggling of this secondary, say in this case 90 degree. This is 90. This is 180. So 90 degree of the total period. So what happens now is, due to this shift, I'm now picking the current, this current here, and now since this is now reversed, I'm seeing this current, but in the opposite direction. So I2 is now positive here and positive here, and I get an average current. So what we see here is, by toggling this secondary, the output side, we can control the current that is going here. And in this particular case, it's still a short. And then the phase shift is really controlling the average current. In here, the zero phase shift, we got zero average current, and here we got some average current here and here. These are positive current going this way. So this is the idea behind the dual active bridge. So let's go one step further in order to see how we can get the nature of the relationship between current and voltages, etc. And here I'm going to do a trick, you might say, of simplifying the analysis rather than trying again writing equations, and as it turns out they are really lengthy. I'm doing the following. I'm describing the system as two square waves. This is the bridge at the input, this is the bridge at the output. They are producing a voltage, square wave of a voltage. And this voltage is imposed on an inductor in between. Now, we can see here, we can understand now that if these two are in phase, they are together high, together low, and there is no average current here. If, however, there is a phase shift, there could be a current flowing one way or the other. Okay, now I'm doing a second step, and the step is as follows. I'm going to do a superposition of two cases that is describe this. And the superposition is done in this way. I'm assuming a short here and seeing what is the current that is flowing here. And then I'm shorting here, the primary, and seeing what is the current that is flowing here. So here it is. This is the case that the VCD is shorted, so I see the current here. And this is the case that VAB is shorted, and I see the current here. The idea is that if I know this current and I know this current, then the actual current in the inductor is the sum of these two. Why I'm doing this? Because it's very simple to look at each of these rather than to look at the complex when you have two square waves which are shifted. That it becomes really complicated. Here it's simple. And here it is. This is VAB and this is VCD. This is the secondary, and they are shifted. Now, VAB is causing a current. This is the current that VAB is causing. Its own current. VAB is causing here a current. And I'm now concerned with the current here and here that will be eventually. Now I'm in a stage that I'm looking at the current due to VAB itself, and this is this current. The average current contributed is 0 to here, because for this side here I have on all the time, this is 50%, and therefore since this current is going from minus to plus and these areas are equal, then of course the contribution of VAB to its own current is 0. So what I'm left with is the question, what is the contribution of VCD to VAB, or to the inductor, you might say. Now again, VCD by itself, I'm sorry, this is an error here. This should be actually going on here like this. So for VCD, its own current is also starting, well, in this case it's just reversed, as a triangle. Here it is. So VCD, again, the contribution to itself, average current, is 0. But if you look now at the contribution of VCD, of this current waveform, to VAB, it becomes obvious that the contribution is not 0, because during this time the VAB sees this current here. this part here, this one and this one. And therefore, there is an average current here, not like this. This one is 0, but here we have an average. It is rather simple to calculate the area here, which is the average current. I mean, just the area divided by the length. This will be the average value. And this is based on the fact that, first of all, these two triangles are equal, similar. And this is the phase shift here. This D is in terms of duty cycle, this is the phase shift. And this part here is a symmetrical triangle, so therefore this is also the same distance here. From the time here, which is this time, which is left after twice this time, we can find what is this x. So once we know this height. So now this area is this rectangle and the triangle here. I'm not going to do this, it's just geometrical calculation, rather simple. And once you do this, you get the average value of the current contributed to VAB. Let me just go back for a second. 1 minute. Let me first of all clarify here that we are talking about this current, which is contributing to the average, because this and these cancel out. This is negative for this and this is positive for this. So now let me just go back and reiterate what I did. I looked the contribution of this current to this current on VAB, which is, this one is shifted, so therefore it is contributing an average current to VAB, and this is the average current. And it turns out that if you do this calculation, you find that the current to the primary contributed by the secondary is equal to this expression, very simple, and duty cycle is defined by this time over the total period, okay, total period here or period here. This is the period, and therefore we see that the output, the input current is a function of the output voltage, some constant G. This is this G here, this value. It is TS, the duty cycle, the period, times minus D, this again, this duty cycle ratio, times D. This product, by the way, has a maximum at D is 0.5. And then N is the turn ratio of the transformer, which I've now taken into account, because in between the primary and secondary there could be a transformer, and then you have to take into account the turn ratio, which is N, and then L is the inductance. So this comes out to be very interesting, that the input current is a function, linear function of the output current. Now I'm going to another subject, which is called a gyrator. What is a gyrator? I just copied it from Wikipedia. A gyrator is a passive, linear, lossless, two-port electrical network element proposed by Telegin. It's a hypothetical fifth linear element after resistor, capacitor, inductor, ideal transformer, and then we have the gyrator. There's no element, physical element, that is a gyrator, but you can build a circuit that behaves like a gyrator. Now there is also a symbol that already been attached to it. Here is the symbol. This is gyrator, and the unique feature of the gyrator is that it is the transfer ratio or the relationship between the voltage and current are according to this matrix, which means that I1 is G times V2 and I2 is equal to minus GV1. Now, the conventional way of presenting the direction of currents in a two-port element is current coming in. So I2 is also coming in. In reality, it's coming out, because if you have a power coming in, then the power is coming out. But this is non-storing power element. So, however, the convention is to use this I2 to this direction. So this is a generator. We have already found that the current at the primary is indeed G times V2. So what about the secondary? Well, it turns out that if I1 is G times V2, then because P1 is P2, it's a lossless divide, that is V1, I1 is V2, I2. Now instead of I1 I write GV2, these cancel out, and you find that I2 is also GV1, exactly as we have it here. Missing is of course the minus, because we have assumed the direction outside, as like in power electronics, the power is coming out, it's not coming in. So this is this reason for this minus, and G is this fraction, this expression, and it's very simple. So this means that if you shift the phase, you get this kind of a relationship. It's really, there's a question, what is the starting point? So there might be plus minus 180 degrees here. But obviously, there's no priority to one side over the other. That is, if you have this, and if the phase will be reversed, then you'll have power coming from the output to the input, because of course it's entirely symmetrical. So therefore you get this plus and minus values for G, meaning that's one direction and the other direction. Now what about power? Second, I'm sorry here. Now what about power? Power is V2 I2, output power, or I2, V2 is I2 over RL. RL is the load, so therefore power is I square RL. So we can find that the power now is also coming out for a given RL proportional to the square of the input voltage. That is, you can control the power by changing the input voltage. It'll be according to this equation. So this, up to now, we talked about the very basic operation. Now some of the advantages. We already talked about bidirectional because it's totally symmetrical. And now what about zero voltage switching? Now what is zero voltage switching in this context? If we have a half bridge and say the upper transistor is on, there is a current flowing this way, say, and then you turn it off. If this is off, then the current will find its way to go through here. Obviously, you need a dead time not to have a shoot through. But during the dead time, there is a diode, either a body diode or an external diode, and the current will pass through the diode. And then you can turn on the transistor under zero voltage switching, which is through zero voltage switching. Now the upper transistor is turned on what I call pseudo zero voltage switching, because for the upper transistor really happens if you turn it off very quickly in terms of current. You turn the current off very quickly if you have a very strong driver that will pull down the gate very quickly and absorb all the charges from the gate. Then due to the output capacitance of the transistor, or you might actually add some capacitance, the voltage of the capacitance will go up a little bit slower. So therefore the overlap between the current and VDS of this transistor, this upper transistor, is relatively low. So therefore it is sort of a zero voltage switching, which I call a pseudo zero voltage switching. For the lower transistor, in this case, it's absolutely a zero voltage switching. So this is one advantage of this topology. And we can see that we have zero voltage switching because as we say switch down S1 and 4, there is a current. So this current now will pass through this S2, S3. That is, we had S1, S4 contacting, we turn them off, the current of the inductor will then clamp into the upper transistor. There is a diode, either a body or external diode, and same thing goes for the S3. So therefore, it is a zero voltage switching, so therefore the switching losses are relatively low rather than hard switching in a regular PWM. Now, what I've shown is a very basic and conventional modulation method. There are many other methods. This is the one that we talked about. Here is the primary, this is a VAB of the primary, VCD of the secondary, and here is the shift. Now you can think about a modulation like this. This is the secondary, and here is the primary, which I'm sort of shorting it and not necessarily leaving it 50% over the period. Okay, so, and then there is another way, and then here is still another way. So there are many ways. It's not the only one. So there are very many possibilities here. Now, why would I like to try other possibilities? Because these provide some advantages in certain applications. For example, they might extend the zero voltage switching range. They can also provide, again, the basic dual active bridge has a gain of 1, excluding, of course, the transformer turns ratio. You cannot get an output which is higher than the input if the transformer is 1-to-1. And with certain modulation method, you can actually do it, because then you can operate it like a sort of a boost converter. It has, of course, its own disadvantages. I'm not going into it in this introductory presentation. Now, finally, I'd like to talk about the resonant dual active bridge topologies very briefly, just to mention them. They are very important, and this is actually the way to go now. And the difference would be that rather than having an inductor which is causing a triangular waveform, to add a capacitor, and therefore you're going to have a resonant waveform, a resonant current. And I'm showing here a very unique case, which is actually excellent, in which the resonant frequency is exactly this frequency of the excitation of the square wave at the input, and then it fits exactly. So when you toggle these transistors and these transistors and these transistors, you toggle them under both zero voltage and zero current switching, which is excellent. And of course the switching losses will be much lower. Now obviously for control you'll have to change the frequency, and then of course you'll have in some cases partial what I call pseudo zero voltage switching, but it's life. But in cases, and there are cases that you like to have just a one-to-one isolation, that is, suppose it is, of course, an isolated version. Let me go over here where it is. Isolated version, you like to have it one-to-one, and by adding a capacitor and tuning it, you can work at resonant, at zero voltage, at zero current switching, which is of course very nice, and the efficiency will be very high. So this is the advantage of using the resonant, which is a subject by itself. Perhaps I'll prepare a tutorial on this in the future. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it interesting, and perhaps it will be useful to you in the future. Thank you very much.